Okay, problem 4.21. I'm going to draw out the situation, and then we'll break it down. Read the problem, and we'll go from there. Hope that your day is going well as you're watching this, and that if not, maybe this cheers you up a little bit. Okay, so problem 21 says, a certain coaxial cable consists of a copper wire, radius A, surrounded by a concentric copper tube of inner radius C. The space between is partially filled from B out to C with material of dielectric constant epsilon sub r, as shown. Find the capacitance per unit length of this cable. So we want capacitance per unit length. That's what we're after here. And we've got copper here, right? I want to just make one up to kind of visualize the situation better. They only give us the inner radius of the copper tube, but just to kind of help us understand the situation better, to visualize it better, I'm just going to make up some outer radius for this copper tube. Call it R. And from C to R, you also have copper. Now, as the problem tells us, from B out to C, right, we've got dielectric material. Dielectric. And by looking at the figure Griffiths give us, you can see that from A to B, got vacuum. Okay. So, like I said, we need the capacitance per unit length of this cable. All right. So we know that this is the formula for capacitance, right? If we have a parallel plate capacitor, we know that one of the plates has positive charge, the other one has negative charge, and there's a potential difference between. So for this situation, I'm going to denote that the copper wire has the positive charge. And the positive charge is distributed on the surface of the copper wire. Because copper is a metal, so we've got a conductor here. And we know for conductors, excess charge is distributed on the surface. So this is analogous to like the positive plate for my parallel plate capacitor analogy I've drawn. And similarly, there's negative charge distributed on the inner surface of the copper tube. Again, this charge resides on the surface because copper's a metal, so it's a conductor. And we know that for conductors, excess charge resides on the surface of the conductor. And if you draw a little Gaussian cylinder for yourself, you can convince yourself, right, of two things. So we know that E is 0 within the conductor. So that means that on the inner surface of the copper tube, the amount of negative charge there is equal to the amount of positive charge on the surface of the copper wire, right? Because since E is 0, Q enclosed must also be 0. And this also shows you why specifically the negative charge is distributed on the inner surface of the copper tube. Because if it wasn't, E inside the conductor would not be 0, which we know is not true. Because there would be some net Q enclosed, namely the charge on the surface of the copper wire. Okay, so that's just a little bit of background to understand why everything is the way it is. So, what we really need to do is find the potential difference between A and C, right? We'll use this handy-dandy equation. Find this potential difference. To do this, we really need the electric field in two regions. The electric field is vacuum region, and the electric field within the dielectric material. Okay. So, I'm going to use, first, let's find the electric field in the vacuum region. Okay? To do that, what I'm going to do is I'm going to draw a Gaussian cylinder, because we're going to use Gauss's law. Here's good old Gauss's law. Using the Gaussian cylinder I've drawn in blue as my Gaussian surface, note that this is equal to Q enclosed over epsilon naught. In this case, Q enclosed is the charge on the surface of the copper wire. We know that this Q enclosed will be equal to surface charge density on the surface of the copper wire, right? Or I guess more precisely, I should say the surface charge density of the copper wire. Either way, Q enclosed will be the surface charge density of the copper wire times the area of the copper wire, which is 2 pi LA. We're saying that the copper wire and the copper tube, in fact, the whole cable has length L. That's where I got the L from. Okay. So, simplifying this equation, you can write that E times 2 pi LS is equal to our Q enclosed, which is sigma times 2 pi LA over epsilon naught. Further simplifying, we find that evac is equal to, you can see that this 2 pi L cancels. So evac is equal to sigma A over epsilon 0 S in the S hat direction, right? Because of the symmetry we have, we know that the electric field is radially outward. And because of the symmetry we have in the situation, that's how I was able to go from rewrite this integral like I have it here. Okay. Now, we need to find the electric field within the dielectric material. Now, to do this, we can't use this form of Gauss's law. And it's very subtle why. I'm just going to go over it briefly. But within the dielectric, we have bound charge. We don't know what the bound charge is, right? We have no idea. And so if we use this, we wouldn't fully know Q enclosed, because Q enclosed would enclose both the free charge on the surface of the copper wire and the bound charge within the dielectric. But again, we don't know the bound charge. So to find the electric field within the dielectric material, we use this form of Gauss's law, right? Because this is equal to Q free enclosed. And we know Q free enclosed. It's actually this quantity right here. So, again, let me draw this out. For this situation, this would be my Gaussian cylinder I'm using. Okay? So, because of the symmetry of our situation, you can write this like this. simplify Gauss's law. And Q free enclosed is sigma 2 pi LA. So the electric displacement within the dielectric material, again, this factor of 2 pi L cancels, is sigma A over S in the S hat direction. It's radially outward, and we can reason this because we know that electric field points from positive to negative. And that means that the electric field within the dielectric is going to be in this radially outward direction. And we know that electric displacement then must also be in that direction because of this equation, which is actually what I'm going to use to find the electric field. From this equation, you can see that E and D must be in the same direction. And using this equation and the electric displacement I've just found, the electric field within the dielectric is then equal to D over epsilon. And I can write this as like so, right? Because we know that epsilon is equal to epsilon 0 times epsilon r. Okay, so I have both fields that I need. Now let's find the potential difference. Go from A to C, E dot dl. Go from A to B, E vac dot dl minus B to C, E dielectric dot dl. I'm going to take a radial path, so my dl is just going to be S hat ds. And I'm going to rewrite this equation because I really only need the absolute value of the potential difference. So taking that into account, V is just integral from A to B, E vac dot dl plus integral from B to C, E dial dot dl. Okay, let's plug in what E vac and E dial are. So I can write this as integral from A to B. E vac is right there, so it's going to be sigma A over epsilon 0 s ds plus integral from B to C. E dial, we have it right here. So it's going to be sigma A for S epsilon 0 epsilon r ds. Okay, let's keep going. So I'm going to get a natural log out of both of these. It's going to be sigma A epsilon 0 ln s, evaluate from A to B, plus sigma A, sorry, that's a mistake, sigma A over epsilon 0 epsilon r ln s B to C. There we go. This is proper, this is correct, this is what we have. Okay? So this is sigma A epsilon 0 times ln B minus sigma A for epsilon 0 times ln A plus sigma A over epsilon 0 epsilon r ln C minus sigma A epsilon 0 epsilon r ln B. Okay, let's do some factoring and use some ln properties to make this simpler. So this can be written as sigma A for epsilon 0 times ln B minus ln A plus sigma A for epsilon 0 times epsilon r. times ln C minus ln B. Doing some factoring and using ln properties, this can be rewritten as sigma A over epsilon 0 times ln of B over A plus ln of C over B over epsilon sub r. This is our potential difference. This is the charge that we're going to use in the capacitance formula. So capacitance is going to be equal to sigma over 2 pi LA over this big expression I've just found, sigma A over epsilon 0 times ln of B over A plus ln of, C over B over epsilon r, and close this parentheses the best I can. I don't have a lot of room. Okay. Doing some cancellation, we get that the capacitance is equal to 2 pi L epsilon naught over ln of B over A plus ln of C over B and over epsilon sub r. So, using this, dividing by L means that the capacitance per unit length is 2 pi epsilon naught over ln of B over A. You know what? I'm going to write this in a different color, and I'm going to write it somewhere where I have a little bit more room. We just found the capacitance, so the capacitance per unit length is as follows. 2 pi epsilon 0, right? The L goes away because it cancels out, over ln of B over A plus ln of C over B over epsilon sub r. And I want to make this B a little bit neater. All right, this is our answer. That's it. Hope you enjoyed this solution.